Okay, let's start our last lecture video about approximated likelihood ratio test and chi-square test in categorical data analysis. So today in this lecture video we have two topics. First one is approximated likelihood ratio test. First topic of today's lecture. The second topic is chi-square test. In categorical data analysis, and this is abbreviated as CDA. So let's first take the first topic of today's lecture. So the first topic of the lecture is approximated likelihood ratio test. So let's review likelihood ratio test statistic. Review likelihood ratio test statistic. Is capital lambda equals, it is a ratio, so the numerator being the sup of theta from the null hypothesis perimeter space likelihood function evaluated at theta divided by the sup of theta from the whole perimeter space capital theta likelihood evaluated at theta. So to perform likelihood ratio test statistic, we need to rewrite the hypothesis as in the perspective of perimeter space. So we need to first write in this way, and then we get the whole perimeter space being the union of the null perimeter space and alternative perimeter space. And we get two steps. First is to write rejection region as such set capital lambda less than k, and how to determine k. To determine k based on the following formula. Determine k, so set alpha equal this probability of capital lambda less than k, this set given each null is true. So given the null perimeter space. So this is the review for likelihood ratio test statistic. So what is approximated likelihood ratio test statistic? So this is our first new topic of today's lecture. So we'll enlarge. There is an approximated test based on likelihood ratio test statistic. Capital lambda as summarized in the following summarized in the following theorem. So let's see what theorem it is. The theorem is: consider random sample capital X1, capital Xn, IID, some distribution small f, small x given theta, and we have write the original hypothesis in the perspective of parameter space, which is as follows: theta from the null hypothesis parameter space, and each alternative, H1, is theta from the alternative parameter hypothesis. Then what the theorem is? The theorem says under each null, -2 log capital lambda follows k squared r minus r0 1 enlarged. So this is the theorem. So what is r and what is r0? So r is the number of free parameters in the global parameter space. In global parameter space capital theta. So what is r0? R0 is number of free parameters in the null parameter space. So let's say an example of this approximated likelihood ratio test. So let's say example. This example, let's given two random sample capital X1 to capital Xn, ID, Poisson with parameter theta 1, and another random sample at capital Y1 to capital Yn, ID, Poisson with parameter theta 2. And we would like to test H null theta 1 equal to theta 2 and H1 theta 1 not equal to theta 2. So the first step is to rewrite the hypothesis in the perspective of parameter space. So let's rewrite the hypothesis. So H null is, so theta has two parameters, theta 1, theta 2, in the null parameter space. So what is capital theta 0? Capital theta 0, the null parameter space is theta 1 greater than 0, theta 2 greater than 0, theta 1 equals theta 2. So since theta 1 equals theta 2, the number of free parameters are 0 in this null parameter space is 1. So what is the global parameter space? So global parameter space is the union of null parameter space and alternative parameter space. So theta 1 equals theta 2 and alternative is theta 1 not equal to theta 2. So if union these two parameter space, you see that there's no any constraints on thetas. So what is global parameter space? Global parameter space is just theta 1 greater than 0, theta 2 greater than 0. So the number of free parameters in the whole parameter space is 2 due to the above mentioned theorem. And the H null negative 2 log capital lambda follows k square r minus r0. Here r equals 2, r0 equals 1, 2 minus 1 equals 1. So I square with degree freedom 1. So this is our first step. So the second step is to find the specific capital lambda. In this case, what is capital lambda? So second step, find capital lambda. So capital lambda, so let's review the PDF of Poisson distribution. So PDF small x given theta 1 is xi factorial theta 1 raised to the power xi exponential raised to the power negative theta 1, and PDF y given theta 2 is yi factorial of the numerator being theta 2 raised to the power yi exponential raised to the power negative theta 2. So let's write the likelihood function. The likelihood function is just the product. So this time likelihood function has two parameters. Theta has two parameters, theta 1, theta 2. And likelihood function is just the product of PDFs. So I from 1 to n, f small f xi given theta 1, small f yi given theta 2. When we plug in the PDFs of Poisson distribution, so we got what? We do some rearrangement. We got the product I from 1 to n, 1 over xi factorial times theta 1 raised to the power summation I from 1 to n xi e raised to the power of negative n theta 1 and times the product I from 1 to n yi factorial, the reciprocal of this, times theta 2 raised to the power summation I from 1 to n yi exponential raised to the power negative n theta 2. So this is the likelihood function for Poisson distribution. And then we can observe that this representation has some constant in it. So to maximize the likelihood function, the constant factor does not matter. So it is a constant times theta 1 raised to the power summation I from 1 to n xi, theta 2 raised to the power summation I from 1 to n yi exponential raised to the power negative n times theta 1 plus theta 2. And what we should do next is that, because we would like to find maximum, partial theta 1, theta 2, partial derivative equals 0, and partial theta 1, theta 2, partial theta 2 equals 0. We'll find theta 1, the MLE is small x bar, and theta 2, MLE is small y bar. This is for under H. This is for the global hyperparameter space. But for end H now, and h now theta 1, h now is theta 1 equal theta 2. Let's write it equal theta star. How to find MLE for the null parameter space. So here only one parameter, L theta star, and the likelihood function you can check is constant times theta star raised to the power summation I from 1 to n xi plus yi times exponential raised to the power negative 2n theta star. So to find MLE, set the derivative of likelihood function d theta star, set this derivative to 0. Then we got what? Then we got the theta star. MLE maximum likelihood estimation is what? A small x bar plus y bar divided by 2. Since we got the MLE for null parameter space and for global parameter space, we can calculate the likelihood ratio capital lambda, which is a ratio of numerator being the sup of theta from null parameter space L theta divided by sup theta from capital theta L theta, and we just plug in our MLE into this representation. So for the numerator, it is the likelihood function evaluated at x bar plus y bar divided by 2. Since under H null, theta 1 equals theta 2, so there is only one parameter. And for the global parameter space likelihood function, we plug in small x bar, y bar, and you can do some simplification, which is simple algebraic operation. Firstly, we plug in. So for numerator, it is small x bar, small y bar divided by 2 raised to the power summation I from 1 to n xi plus yi exponential raised to the power negative 2n x bar plus y bar divided by 2. This is the numerator. Denominator is x bar raised to the power summation I from 1 to n xi y bar raised to the power summation I from 1 to n yi exponential raised to the power n x bar plus y bar. So we got our likelihood ratio, and you can further do some simplification. So this factor and this factor cancel. They are the same thing. And what is left is just this part. This part is capital lambda. And then if negative 2 lambda log capital lambda greater than chi-square with degree of freedom 1, because r minus r0 is 1, alpha quantile, reject H null, otherwise not reject. So this is one application of the approximated likelihood ratio test. So let's review our approximated likelihood ratio test. What it is a theorem. So this theorem is quite useful. So in this theorem, if we have random sample following some distribution, and we would like to test hypothesis in the perspective parameter space. So under H now we have this very useful result. Under H now, the negative 2 log of likelihood ratio is chi-square with degree from r minus r0 while enlarged. And what is r? R is number of parameters in global parameter space, and r0 is number of frame parameters in the null parameter space. I've given to you this example to show the application of this theorem. Okay, this finishes our first topic of today's lecture. So let's see the second topic of today's lecture. So the second topic of today's lecture is chi-square test in categorical data analysis. And categorical data analysis is often abbreviated as CDA. So what is chi-square test in CDA? Let's see. Chi-square test in CDA. Consider random vector sample So the random sample x is capital X1, capital X2, all the way to capital XK. And this random vector sample is for each capital Xi, we can take value 1 with probability Pi and 0 with probability 1 minus Pi. So this is the data generating process assumption. And so the key here is K categories. K categories. And we have two constraints. First is capital X1. This K random variable, we need to make it the summation as a fixed value, small n. So this one is fixed. These are all random variable, but we need to make its summation is fixed as n. And we need to make the parameter p1 all the way to pk. So what is p1 all the way to pk? Remember, for capital Xi, it takes value 1 with probability pi, takes value 0 with probability 1 minus pi. So p1 plus all the way to pk is what? Is 1. So this actually is a generalization. This kind of data generating process let's make a remark. Is a generalization of binomial distribution and we can take a look at its PDF. So its PDF actually has this form. Probability of capital X1 being small x1, capital Xk being small xk. It is in this form is quite similar to the binomial PDF, since it is a generalization of binomial distribution, but it is a little different. Their representation is quite similar. P raised to the power small x1, all the way pk raised to the power small xk. So this is generalization of binomial distribution and is actually called multinomial distribution. Multinomial distribution. So what is chi-square test in this case? So I will introduce to you the chi-square test. So before introducing the test statistic, let's see what hypothesis we are interested in. So the hypothesis we are interested in is P1. We have K parameters. We want to test them simultaneously. So the null hypothesis is P1 equals some P10 all the way Pk equals Pk0. This is our null hypothesis. And H1, the alternative hypothesis, is not H null. So what is chi-square statistic? So chi-square test statistic, we write it as chi-square. Chi-square test statistic is defined as follows. Chi-square equals summation I from 1 to k small fi minus ei squared divided by ei. So what is small fi and what is small ei? So small fi is observed outcomes falling into category 1. Okay, so actually we don't write it as small f, we just write it small x. Small x. So small fi actually is just small xi. So small xi, let's repeat what small xi is in this data generating process. So small xi is observed outcomes falling into, belong to, observed number of outcomes belong to category I. We have K category, so it's small xi. So what is small ei? So small ei is expected number of outcomes belong to category I. And EI is just N P. So N is the summation of all xi. So N is fixed. The summation for the random variable is fixed to N. So if their realization, their summation is also N. So N is summation small x1 all the way to small xk. And EI is under H now is NPI 0. Under H now. Because under H now, PI are set equal to PI 0. Then just remember the fact. Then it is the fact. We need mathematical proof, but we don't do it in our class. The chi-square test define that I from 1 to k small xi minus ei squared divided by ei follows chi-square k minus 1 enlarge. So this is chi-square. So this is chi-square test in categorical data analysis. So let's do a quick review. So for chi-square test in CDA in categorical data analysis, consider random vector sample. So the random vector sample, I said, is just the following. So capital X is capital X1, capital X2 to capital Xk. We have k categories, and each random variable xi is binomial, is Bernoulli, and we have two constraints. The first one is the summation of capital X1 to capital Xk is n. Another constraint is small p1 all the way to small pk is 1. So actually, this data generating process is a generalization of binomial distribution. It is actually called multinomial distribution. Its PDF has similar form to binomial, but we have generalized the binomial case to multinomial case. So then, to introduce chi-square test in categorical data analysis, we have to explicitly write down the hypothesis we are interested in. So the null hypothesis is P1 equal P10 some pre-specified value, Pk equal Pk0 some pre-specified value, and H1 is not H0. So chi-square test statistic is defined as the following. It's defined as this form: summation I from 1 to k, xi minus ei squared divided by ei. And xi is observed number of outcomes belong to category I, and ei is expected number of outcomes belong to category I. So what is ei? Ei is actually n times pi0 under H now. So then it is the fact. You can also say it is a theorem. It is a theorem that chi-square test statistic, writing in this form, follows chi-square distribution. That's why it is called chi-square test statistic. Chi-square with degree of freedom k minus 1. So this is a fact. Just remember this degree of freedom 1 enlarge. So this is chi-square test in categorical data analysis. And chi-square test, let's do a quick remark. Chi-square test statistic in categorical data analysis CDA mainly has 3 applications. So the first one is goodness of fit test. And the second one is independence test. third one is homogeneity test. Let's see these three applications one by one. So the first is goodness of fit test. First, goodness of fit test. Let's see it by an example, specific example. Goodness of fit test using the likelihood, okay, using the chi-square test statistic. Okay, let's consider random vector sample x equal x0, x1, x2, and we need x0 plus x1 plus x2 equals small n, the first constraint. The second constraint is p0 plus p1 plus p2 equals 1. So recall, what is p0, what is p1, what is p2? So for pi, for xi, capital xi, it takes value 1 with probability pi, 0 with probability 1 minus pi, I equals 0, 1, 2 in this specific example. And we make it more explicit. So let's, for example, consider n weeks let's define x0, capital X0, number of weeks with 0 accident. And capital X1, number of weeks. So for n weeks, capital X1 is number of weeks with 1 accident. And what is capital X2? Capital X2 is number of weeks with 2 or more accidents. And we define one more random variable, let capital Y be number of accidents per week. So let me give you some specific value. So the number of weeks, small n, is 50, and one realization of the number of weeks with 0 accident is 32, and number of weeks with 1 accident, the realization is 12, and number of weeks having 2 or more accidents, the realization small x2 is 6, and for the capital Y, the summation, the sample mean, yi, the number of accidents per week, sample mean is 0.48. So this the real data. So we would like to test what? The null hypothesis is capital Y, the number of accidents per week. We would like to test that it follows Poisson distribution. with some parameter lambda unknown. So h1 is not h0. So this is called goodness of fit, because we would like to test one random variable following some specific distribution. So this is called goodness of fit test. And since this is the application of chi-square test, how to apply chi-square test in goodness of fit test. Let's see. So the way is approach, rewrite h0 by interpreting h0 using the principle of maximum likelihood estimation. MLE. Let's see how to apply this principle in our specific example. So in our specific example, we would like to test h0, capital Y follows Poisson, lambda, h1 is not h0. How to do this? So you need to write out the likelihood function of parameter lambda given the data y, small y1 all the way to small yn, and we write it as the product I from 1 to n, the PDF of small yi. So small f is PDF of Poisson distribution given lambda, and you know how to write PDF of Poisson, and then you take derivative, set derivative lambda d lambda 0, then you find what? You find lambda hat MLE is small y bar. Small y bar. So using the principle of maximum likelihood estimate, we rewrite h0. So h0 is capital Y follows Poisson, lambda. Using the principle of maximum likelihood estimate, we find lambda hat MLE. So how to rewrite h0 after we find MLE? So if capital Y follows Poisson with lambda hat MLE, so what is P0, P1, P2? So P0 is the probability of x0 takes the value 1. And P1 is the probability of capital X1 takes 0, 1. If there is one accident in a week? If there's 1 week which has 1 accident, then capital X1 record 1. If there's no accident of some specific week, then capital X0 record a value 1. Add 1 value to capital X0. So by interpreting capital Y with Poisson into our multinomial distribution, what is the relation? So H now is capital Y follows Poisson. So using the principle of maximum likelihood, first we get lambda hat MLE equals Y bar. But we would like to translate this alternative to null hypothesis in the chi-square test statistic. Chi-square test statistic, we write P0 equals P00 some pre-specified value, P1 equals P10, and P2 equals P20. In our original chi-square test, we have PK, we have K categories, but in this specific example, we only have P0, P1, P2, and H1 is not H0. So how to relate these two? Our goodness of fit test hypothesis and the chi-square test hypothesis. How to relate these two? How? We need to use the first step of lambda hat MLE Y bar to calculate this null hypothesis, which means P00 under H null. P00 is what? Is lambda hat MLE raised to the power 0 e raised to the power negative lambda hat MLE divided by 0 factorial. We plug in the value. So Y bar 0.48 raised to the power 0, exponential raised to the power negative 0.48 divided by 0 factorial. So the result is 0.619, and P10 is lambda hat MLE raised to the power 1 exponential raised to the power negative lambda hat MLE divided by a factorial, and you plug in the numbers, you get 0.297. Okay, and for P2, because we have the constraint that P0 plus P1 plus P2 is 1, so P0 is 1 minus P0 minus P1 is 0.084. Then we have successfully rewrite our so the capital Y follows Poisson lambda. If you translate to chi-square test statistic, we have to calculate P00 and P10 and P20. If it in fact follows Poisson, and we find that P00 is 0.619, and P10 is 0.297. and P2 0. Zero point 0.084. So we have successfully translate our goodness of fit hypothesis to chi-square test hypothesis. Then we can apply chi-square test statistic. Apply chi-square test statistic. So let's calculate chi-square test statistic. It is summation of small xi minus ei squared divided by ei. So in this case we have three categories. So small x0 minus n p00 squared divided by n p00 plus small x1 minus n p10 squared n p10 plus x2 small x2 n p20 squared divided by n p20, and we plug in 32 minus 50 times 0.619 squared divided by 50 times 0.619 plus 12 minus 50 times 0.297 squared divided by 50 times 0.297 and plus 6 minus 50 times 0.084 squared divided by 50 times 0.084 and equals 1.354, and compare with chi-square with division on 1 alpha quantile. If it is greater than this one, you can check table, chi-square table. If it is greater than this one, then we reject each null. Otherwise, not reject each null. So this is the first application of chi-square test in the goodness of fit test. To do this, the key step is to translate the goodness of fit testing hypothesis to our chi-square test hypothesis by using the principle of maximum likelihood. So the first step is to get maximum likelihood estimate under the null hypothesis of goodness of fit test. You get a maximum likelihood estimate, and then you translate this to original one. Because original one, the chi-square test statistic hypothesis is in this form. We have to each null for y is really Poisson, you can calculate p00, because if y is really Poisson, we can calculate p00 using the PDF of Poisson distribution, p00, p10, and p20. Then we successfully translate the goodness fit testing hypothesis to chi-square test hypothesis, and then we can apply chi-square test statistic by definition. Then we solve the goodness of fit testing by applying the chi-square test statistic. So this is first application of chi-square test statistic. The first application of chi-square test statistic is goodness of fit test. Goodness of fit test. First application of chi-square test statistic. So let's say the second application, independence test. Independence test. For independence test, let's consider the following random vector sample. Consider the following random vector sample. Capital X is capital X1 1, capital X1 capital J, capital X2 1, capital X2 J, and capital XI 1, capital XI J. So we use small I to denote the first group, small I, 1 to capital I. So the entry of this vector, long vector, is capital small xij, small I, 1 to capital I, and small g, 1 to capital J. So we call and we consider in this independence testing scenario, consider there are two groups. How to consider there are two groups? So let's say for this first row, you can see because for I part it is all 1, and only difference is in the second subscript, the J part. So we can consider this as a group. Okay, let's make it more clear. So xij. So let's first write down the data generating process. Okay. Again, like what I have done for previous example. So xij, we think it takes value 1 with probability pij, and takes value 0 with probability minus Pij. And similarly, we cast constraint. This time we have double summation I from 1 to capital I, small j from 1 to capital J, capital Xij equals small n, and double summation j from 1 to capital J, small I from 1 to capital I, Pij equals 1. Similarly, we have two more constraints, and the data generating process is similar. So, how to consider? So, for the i's level, so this is group 1 has I levels, and this is group 2 has capital J levels. So what is our interested hypothesis? So this is independence test. So our interest hypothesis is group 1 and 2 are independent. And the alternative hypothesis is not H null. So let's further introduce one more notation, pi dot is the probability in ith level of group 1. And another new notation is P dot J is probability in jth level of group 2. So we also need to rewrite H null. So what is H null? H null is group 1 and 2 are independent. So this is called independence test. Independence test. We need to rewrite the H null by interpreting H null using the principle of maximum likelihood estimation. And A, we're using the principle of maximum likelihood estimation. The pi dot, the probability in ith level of group 1, using the principle of MLE is hat. It's simply, we have done this many times. It's just summation j from 1 to capital J Nij divided by n. Sorry, xi, small xij, not nij. small xij, and associated with pi dot, we gave a new notation, this ni dot divided by n. So we apply the principle of maximum likelihood. We have pi hat MLE and p dot j MLE hat. I also have done this many times. We just I from 1 to capital I, small xij divided by n, and we give the numerator a new notation as associated with p hat is n dot n dot j divided by n. So by using the principle of maximum likelihood estimation, we got what? We need to translate this original hypothesis to hypothesis like Pij equals Pij 0. Then we can apply chi-square test statistic. So small I is 1 from capital I, small j 1 from to capital J. How to translate? So the key here is also translate. To make such translation, we first apply the principle of maximum likelihood estimation. We got this MLE, and then we translate. So H now is, so if, to translate under H now, group 1 and group 2 are independent. Group 1 and group 2 are independent, which means Pij equals Pi dot times P dot J. And we want to translate our independent hypothesis testing to chi-square hypothesis testing. So chi-square hypothesis testing in this form, small Pij equals Pij 0 and we have found that under H null of the independence, then we have this relationship. So what is Pij 0? So Pij 0, using the principle of maximum likelihood estimation, under H null it is Pi. So under H null here we just write here 0. And we can using the principle of maximum likelihood estimation, we can do what? Here equals pi dot MLE hat times P dot G MLE hat. So we have got this result here. Just plug in this summation j from 1 to capital J small xij divided by n times summation I from 1 to capital I small xij divided by n. And we also gave them new notation. The summation of j from I1 to capital J we denote it as ni dot to associate it with pi dot hat. And we also gave this summation a new notation n dot j. Keep in mind, this one is also n dot and what? Ni dot. Ni dot. And this one also denoted as n dot j. Dot j. Okay. So then we can translate the independence test hypothesis to chi-square test hypothesis. So H now is now Pij equals Pij 0 Pij 0. Pij 0 is what? Is ni dot divided by n times n dot j divided by n. This is dot ni dot divided by n dot j divided by n. H now. So H1 is not H now. So we have successfully translated our independence testing to chi-square testing. Then we apply chi-square test statistic. So chi-square test statistic in this case is double summation small j from 1 to capital J, small I from 1 to capital I, small xij minus expectation of ij squared divided by eij. So what is eij? Eij is n times Pij Pij 0. And remember as a fact, chi-square equals summation j for small j from 1 to capital J I from 1 to capital I small xij minus eij squared divided by eij follows chi-square distribution. It is a fact. We need mathematical proof, but we don't do that in this course. Chi-square, we degree for them I minus 1 times j minus 1. So this is the application of chi-square test in the independence testing. So like what we have done for the first application, which is goodness of fit test, we also first translate the independence testing to our chi-square testing hypothesis, like in this form. And the translation is in the principle of maximum likelihood estimation. The first step, get maximum likelihood estimation, and then we apply the principle, and then at H now we translate the independence hypothesis to our chi-square test hypothesis, and then we apply chi-square test statistic. So this is second application of chi-square test statistic in CDA, in categorical data analysis, independence test. So let's see the third application. Third application of chi-square test. And the last application of chi-square test is homogeneity test. Homogeneity test. So for homogeneity test, we also have the random vector sample. X, have the data, have x11, x1j, xi1, have capital ij, and the entry of this long vector is denoted as capital Xij, I from 1 to capital I, j from 1 to capital J. We have two more constraints. First one is summation small I from to 1 to capital I, small j from 1 to capital J, xij equals small n. Again, capital Xij takes 1 with probability Pij, takes 0 with probability 1 minus Pij. Another constraint is j from 1 to capital J, I, small I from 1 to capital I, Pij is 1. Like for independence test, the data generation process is the same, but our interested hypothesis is like this. This time we do not need to translate. This time it is straightforward. Our hypothesis is we are interested in such hypothesis, Pi1 all the way to Pij equals Pi0, I from 1 to capital I. We are interested in testing such hypothesis. So that's why it is called homogeneity test, because it is testing the equality of those Pi1 all the way to Pij. This is some pre-specified value. So H1 is not H0. And this is called homogeneity test. Homogeneity test. So for homogeneity test, we just directly apply the chi-square test statistic. But before that, we need to calculate the MLE, because under H now, Pi1 all the way to Pi capital J equals some pre-specified value Pi0. is some pre-specified value, and we need to get the MLE of this quantity. So in fact, the pi0 hat, the pi dot. Remember what is pi dot? We have defined pi dot in the previous exam application. So pi dot. Pi dot is p in the ith level of group 1. So for the probability of ith level of in group 1, they are the same across all levels of group J, group 2, which means in fact just accept as a fact. Actually, you can derive by yourself using the principle of maximum likelihood. The pi0 in this case, under the h null, when h null is true, pi0 should be pi dot MLE hat. Let's review what is pi dot. Pi dot. So pi dot is in ith level of group 1. Yeah. And we have done this in the previous application. We just write it down, repeat it. We have done this in the second application. So there's no new thing. I dot. You know what is ni dot divided by n. I dot, we have this is notation. So what is ni dot? Ni dot is summation x small xij, j from 1 to capital J, divided by n. Why we would like to calculate pi0 under h null? Because we would like to apply the chi-square test statistic. Because under h null, what is eij? Eij is actually n dot j n dot j times pi0, and we have pi0 as ni dot divided by n. So let's write it explicitly. So n dot j is summation I from 1 to capital I, small xij. And for this, and for pi0, we got this summation xij, j from 1 to capital J divided by n. We know how to calculate eij. So then we apply chi-square test statistic. Summation j from 1 to capital J, summation I from 1 to capital I, xij minus eij squared divided by eij, following chi-square. So what is the degree of freedom of this chi-square distribution? It is also I minus 1 times j minus 1. And this is, remember, as a fact. It needs mathematical proof, but in our course we don't prove it. Okay. Now we have finished the third application of chi-square test, which is homogeneity test. Okay, let's do a quick review of today's lecture. Today's lecture we have two main topics. First one is approximated likelihood ratio test. Second is chi-square test in categorical data analysis. For approximated likelihood ratio test, we first review what is likelihood ratio test statistic. Likelihood ratio test statistic is capital lambda with being likelihood ratio. You have to maximize likelihood function with respect to null Programming space and maximize likelihood function with respect to the global Programming space. So you first need to rewrite the hypothesis in the perspective of Programming space. You write it this way, then you get rejection region in this way, and determine K by this formula. So when n large, there is an approximated test based on likelihood ratio test statistic capital lambda, as summarized in the following theorem. This theorem needs some rigorous mathematical proof. We don't prove it, we just state the result. The result is a random sample RID from some distribution with x given theta. We have rewritten the hypothesis in the perspective of parameter space in this way. Then under H now, -2 log capital lambda is chi-square with degree freedom r minus r0 when n is large. So what is r? R is degree freedom, the number of free parameters in global parameter space. R0 is number of free parameters in null hypothesis. Then we give you an example of this test. H now theta 1 equals theta 2, H1 theta not equal to theta 2, when two random samples follow Poisson. So we firstly rewrite the parameter space, and we find the number of free parameters in null parameter space and global parameter space, and apply the theorem. And H naught -2 log lambda is chi-square with r with 2 minus 1 with degree freedom 1. So the key issue is to find capital lambda. To find capital lambda, review PDFs. So likelihood function is right in this way, and you can plug in the PDF of Poisson distribution, and you get this maximum likelihood estimate under H now, and this is the global maximum likelihood estimate. And H now, when the two parameters are assumed equal, you rewrite the likelihood function and do maximization. We get MLE. Then we plug in this maximum to numerator and the maximum to denominator. We get likelihood ratio capital lambda in this form. Then we use the theorem that -2 log lambda capital lambda greater than chi-square with a degree from 1. Alpha quantile, we reject H now, otherwise not reject. So this is the first topic of this lecture. The second topic is chi-square test in categorical data analysis. We often abbreviate categorical data analysis as CDA. So chi-square test in CDA, we consider random vector sample. So we introduce one new data generating process. It is like this. So X, we have K categories, so capital X1 to capital XK. Capital Xi is Bernoulli random variable, but we cast two more constraints. First is the summation of capital X1 to capital Xk is n fixed, and the summation of probability is 1. So let me tell you, this data generating process is a generalization of binomial distribution, which is called multinomial distribution, and its PDF is actually in this form. It's quite similar to binomial distribution. And for chi-square test statistic, we are interested in testing such hypotheses. So H now is P1 equals P10, Pk is Pk0. H alternative is not H now. So chi-square test statistic is defined as the following form: the summation of xi minus ei squared divided by ei. So xi is observed number of outcomes belong to category I, and ei is expected number of outcomes belong to category I, and ei is computed as npi0 and H now. So then we have a theorem that this chi-square test statistic following as chi-square with degree of k minus 1 when n large. Remark: chi-square test statistic in CDA mainly has three applications. First is goodness of fit test. Second is independence test. The third is homogeneity test. The first goodness of fit test is that we consider an example of first, for these three categories we have these two constraints, and we give an example. Consider n weeks, x0 number of weeks with 0 accident, x1 number of weeks with 1 accident, x2 number of weeks with 2 or more accidents. So let capital Y be number of accidents per week. Then we have this data. So goodness fit test is interesting in testing that if H now capital Y is following, for example, Poisson with some unknown parameter lambda, H1 is not Poisson. So how to apply chi-square test in goodness fit test? So our approach to firstly rewrite H now by interpreting H now using the principle of maximum likelihood estimation. So H now is this, and we write the likelihood function. and we find that lambda hat MLE is y bar. So how to translate this original hypothesis to our chi-square test hypothesis? We have got the MLE estimate for lambda. So for h null is true, we can calculate p00, p10, and p20 because we assume that the null hypothesis is true. Null hypothesis tells us the distributional information. We can directly apply the distribution PDF. We can calculate p00, p10, and p20. Then we can directly apply chi-square test statistic in this way. So we have solved the first application, which is goodness of fit test. The second application is independence test. Independence test, the case a little complicated. We introduce one more new data format. For this X, we have this. So group 1, so the long vector has entry as xij. So small I denotes the group 1. Group 1's small I level. And small j denotes the group 2 small j's level. xij is also the Bernoulli form, and we also have these two constraints. So independence test is interesting, testing that group 1, group 2 are independent. H null is not H alternative is not H null. So how to translate this independence test to our original chi-square test? Chi-square test is in this form. So we first introduce two new notation. First, pi dot is in nth level of group 1, the probability, and p dot j is in jth level of group 2. And we also applied the principle of maximum likelihood estimate. We get pi dot this probability, pi dot MLE hat, by writing out the likelihood function and make maximization. You can derive by yourself after class, but it's not required. So without proof, we got this pi dot MLE is ni dot divided by n, which is summation of j from 1 to j, capital Xij. And for p dot j hat MLE is also in this form. So then we can translate the original hypothesis is group 1 and group 2 are independent. So the independence here applies here, this multiply. So Pij0 is Pi dot 0 times P dot J0. If we plug in the maximum likelihood estimate, Pi dot MLE hat, P dot J MLE hat, and we plug in the result, then we translate our original independence null hypothesis to this form, Pij equals Pij dot, which is Ni dot divided by N times N dot J divided by N. H1 is not H null. So we can apply chi-square test statistic in this form. Then we have double summation xij minus eij squared divided by eij. Eij is n minus pij0. So pij0 we already have. So fact, this chi-square test statistic has this degree of freedom. This needs mathematical proof, but just keep in mind it's okay. We don't prove it. So the third application, homogeneity test. Homogeneity test is the same data format, same constraints, but the interested hypothesis is different. We're interested in testing the null hypothesis in this format, that pi1 all the way to pi capital J equals some pre-specified value pi0. So and H null, so it is the H null. So we also apply the principle of maximum likelihood estimate to get pi0 because we don't know what the true value of pi0. Pi0 is unknown. We need the maximum likelihood estimate is pi dot MLE hat, and is ni dot divided by n. And eij is n dot j plus pi0. The pi0 we have had, and n dot j we have defined in the previous example. And so plug in, and then we got the chi-square test statistic in this format. And this degree of freedom is also the same as the independence test, and this also needs mathematical proof, but just keep in mind, accept it as fact. Okay, now we have finished our introduction to theory of hypothesis testing. Okay, thank you. This closes the whole semester of knowledge of classical statistical theory, which can constitute two parts. First is theory of point estimation, and second part is hypothesis testing. Okay, thank you for your cooperation this semester.